Okay, sorry for the interruption. Okay, so coming back to this. Geiger counter. Okay, detects radiation. Now, it's important to understand that often the word radiation, I would say, has a very negative connotation. Right? Normally when you think of radiation, what do you think of? The whole nuclear bombs, cancer, right? Not good things. Okay? Scientifically and by just definition, radiation is actually just a form of energy that travels in a wave. So technically light is a type of radiation. So there's a very big spectrum of good radiation, or not good, but non-harmful radiation, and then there's definitely the harmful side of radiation, right? So just because it's beeping this much doesn't particularly mean like all of it is bad. Today we're going to talk about 4 types of radiation, so what this might be picking up, and why some of it we should be concerned about, and others we're okay. So there's a table right there if you go to where it says Notes 5, and we'll start there. The first type of particle that our device could be picking up is something known as an alpha particle. Okay? The Greek symbol for alpha kind of looks like a fish, is the way I think of it. So you put this in the little parentheses. That's the Greek symbol for alpha. You'll find in chemistry we use a lot of Greek symbols for things because we've already used all the letters for elements, right? Okay. What an alpha particle is an alpha particle is actually, this is the next column, a helium nucleus. Okay, so show me on your fingers for a smiley face without saying anything out loud. How many protons does helium have? Show me on your fingers. Good, if you're showing me 2, you may have a smiley face. You're correct. Good reminder, right? That's just the blue number up top. So an alpha particle, if we could blow it up to size, an alpha particle looks something like this. A helium nucleus, meaning it has 2 protons, and in this case it's helium-4. So 2 neutrons, but no orbiting electrons. So sometimes that's what's causing this to beep as an alpha particle. Goes in that little chamber, and it detects it, beep. So on and so forth. Okay, we'll talk about these as we keep going. But let's write it is that the next column, symbol? Oh, mass. Oh, symbol. Okay, the symbol, so this is the Greek symbol. The chemical symbol is this, He. It has a mass of 4, hence the 2 protons and 2 neutrons. Okay, it doesn't have any electrons. So if I have 2 protons and 0 electrons, oh, close, there you go, +2. Yeah?
Does it matter if it's +2 or 2 plus?
Not really. The most correct way is you actually in chemistry put the plus after the 2 because it's signifying a charge, not like a positive numerical value because there's like a difference. But I don't care which way you write it. So, good question though. Okay, so there's our symbol. Oh, the bottom number here would be 2 because that's how many protons it has. Okay? So here's our symbol. So then we already answered this. The mass of it is 4. If you want to make a note to yourself, remember that the top number on our symbols is always the mass. Okay? The charge is 2 plus 2. Once again, charge is always written on the symbol in the upper right corner. Okay? Okay, now let's talk about what can protect us from an alpha particle, right? So if someone were to come at you with an alpha gun, what type of shield would you need to protect yourself? A piece of paper.
You want us to put that in an example?
Did I skip something?
There is.
Oh, yeah. Put it as example. Maybe put example / power. I don't know why it says example. So when we talk about bad radiation, alpha particles is not what we're worried about, because literally, if you just hold up a piece of paper, you can't get through. So, what does that mean if it's beaming? It means it's not an alpha particle, right? Right, so if it goes through the paper, then it has to be something else, because alpha particles are fairly harmless. Honestly, what happens to most alpha particles, okay, it's one of these, right? So it's pretty much helium without any electrons. It flies around, finds electrons from things, steals it, and then floats up to the atmosphere, because it's helium. So that's pretty much where all the alpha particles go, is they just float away into the universe, right? Okay, very good. Questions on an alpha particle? Yeah, Benson. Tell me this, if the alpha particle can be stopped by a piece of paper, do we have to worry about them penetrating us? No. Right, they can't even pass through our bodies, right? Beep, yeah, bounce right off, right? So if someone comes out with you an alpha gun and says, give me all your money, just walk away, right? Okay, good question though, Benson. Okay, next type of particle we have is a beta particle, okay? The Greek symbol for beta is a B with like a tail. So it's actually not the letter B, it's the Greek symbol beta, but it looks like a B. Okay? A beta particle is like an electron. Okay? So let's talk about its symbol here. So the symbol is, we're going to do a lowercase e to signify it's an electron. Now what do we know about electrons? Good, so we know it's negatively charged. And they have pretty much zero mass, so we are going to put it as a 0. It's not truly 0, right? But it's so close to 0 in this case that we treat it like a 0. Okay? Now here's kind of the interesting part with electrons, as in this we're talking primarily about the effect of the nucleus here. And we'll talk about how are electrons even in the nucleus, because we talked about that they weren't. Okay, let's fill this in, I guess, first. So the charge is 0. The mass is 0. The charge is -1. Down here, we're going to put also a -1. What does this bottom number typically indicate? The number of protons, right? So for electrons, it's a -1 proton value, right? Because they're in a sense the opposite of it. Okay? All right, penetration ability. Beta particles can pass through paper, so that won't protect you. But you'd be pretty safe if you got some lead. Other metals actually might be able to stop it depending on how thick it is, but lead would for sure keep you safe. This is why in terms of radiation, whenever you get, how many of you guys have an x-ray of any kind? I guess hopefully everyone, because I'm a dentist. Right, you have x-rays at the dentist. What do they put on you when you get an x-ray? Yeah, big heavy blanket or vest, right? That is made with lead inside of it. The whole point is they don't want the radiation to go through the other parts of your body. Because even though, yes, x-rays are good to find things, they're not good in too much amount. That's why certain parts of your body nowadays, because now we know better, they won't ever x-ray, right? Like typically your head, they won't ever x-ray heads anymore. What do they do instead? Like an MRI or a CAT scan, because those work differently, right? Same thing, like when I was pregnant last year, they won't ever take an x-ray while you're pregnant, because they don't want to send those through the baby. Sadly, they used to not know the dangers of radiation, and so way back when, they used to x-ray pregnant women to actually look at the baby. But then it ended up sadly in like birth defects and stuff like that. And so now that's why they use ultrasound now, right? Because that literally works just through sound waves, which is safer. So lead is what stops our beta particles. Now, in terms of our danger to us, beta particles aren't super dangerous because they're still relatively big in comparison to us. They can pass through us, but the danger is if they can start changing things. Once again, kind of the idea of the Hulk. Not saying you'll turn into the Hulk, but radiation can change your cells, which is why it leads to cancer, right? Okay, questions on beta particles? Okay, what's the next one? Positron?
Yes.
Okay. Okay, positrons. Well, okay, let me see. This sounds weird, but what it is literally a positron. Positrons are little particles, okay? And in a sense, they are opposite of a beta particle, okay? So the symbol, we still use the beta sign, but we put a little plus on it. This is going to sound really bizarre, but they're kind of like positively charged electrons. But it's not a proton. Because, so we still use the little E sign. Big difference here of why they're not a proton is their mass. They have zero mass, just like an electron.
So this just writes everything we've learned in junior high.
Pretty much.
Alright.
Yep. You're welcome. Okay, but now the difference is, that's going to be a little plus one. And then their charge is positive. Now, side note with charges, if the charge is a 1, you don't technically have to write the number 1. You can just write the sign, kind of like in math, how with x, you don't have to write 1x, you can just write the x. But if you choose to write the 1, that's fine too, okay? Okay, so their mass is 0, their charge is positive. Any guesses based off patterns here of maybe what would stop a positron? And think of the power of them as a lot of times based on their sizing. So since these are the same size, they get stopped by the same.
What?
But that's a great connection. Note that the penetration ability isn't based on their charge. It's just based on their size. The smaller something is, the easier it can pass through, right? Okay, last one, gamma. Okay, the gamma sign is kind of like the alpha sign or a fish, but now it's swimming downward. It also maybe looks like a weird Y. So that's the symbol for gamma. You don't really have to be perfect at drawing these, just recognize if you were to see it, know what it's telling you, okay? Gamma radiation is energy. Pure energy here. So let's come back to the symbol and skip to mass. If it's pure energy, does it have mass? Nope. Right, because energy doesn't classify as matter, and so it doesn't have mass, right? Has no mass. Has no charge, so its symbol looks like this. We actually keep the Greek symbol, and then it's just 0, 0. And since this is the highest energy, pure energy, it has the strongest power. This is the type of radiation we try to avoid. In order to stop gamma radiation, you need a combination of lead and concrete. Have any of you ever watched or seen those previews for like those doomsday people show? Like bunkers and stuff like that? Have you heard those? Right, there are the people who are worried about the end of the world, so they build this bunker somewhere. Anyways, I don't watch them, but I just find it interesting because a lot of times what they build their bunkers out of is a combination of lead and concrete. Because they're trying to protect themselves if there was ever a nuclear war, to protect themselves from the radiation. So, Simply yes. We'll talk more about the dangers of radiation in a later unit when we talk more about nuclear power.
So there's really only 4 radiations?
No, there's more. This is just the
Like,
4
there has to
main
be.
ones we're going to start with.
Okay,
So,
I was like,
yes.
wait.
Yeah.
Okay, so
Oh. You're so
okay,
nice. Go.
scientifically speaking,
Yeah.
could the Hulk actually happen in gamma rays?
So the idea behind it, the idea behind it isn't like it's really cool. There's actually a lot of science blended into like the Marvel series where there's like truths.
Amazing.
Oh yeah.
But in terms of it actually like, because it does change your DNA, right? Like that's how people get cancer from gammas. But what's cool is it's also used, gamma radiation is also used in cancer treatment as well. So a lot of times they'll do gamma radiation to try to kill the cancer cells, right?
Use the cancer to get rid of the cancer.
Yeah.
Nice.
But that's why it's so hard on people's bodies a lot of times too, is because gamma radiation can't tell the difference between a good cell and a bad cell, right? So you're just attacking everything.
Wait, so is chemotherapy?
Chemo's different. Chemo's a chemical that they use. So a lot of times with radiation, they don't send it through the whole body. They isolate it to exactly where like the tumor is. They'll just like shine it right wherever it is on their body. So yeah, good question though. I don't know. Did that answer your question?
You didn't answer it.
Well, no. But there's some truth behind it.
Maybe.
Maybe.
It's a maybe.
Maybe.
We don't know. And I
You
don't
know-
think we want to know.
Really with science, sometimes I say maybe, because there really is like, there's things like 100 years ago they probably like thought never would have happened, right? Like, oh, you'll never be able to do that. And now we can, which is crazy. But yeah, Jeremy and then Carter.
There are like things called megatrons, which are like electrons, but with the mass of a proton.
I've never heard of a megatron.
A negatron.
Oh, a negatron.
It's like a positron, but it's an electron with the mass of a proton.
Well, what? It's an electron?
Yeah, because the positron is like a proton with the mass of an electron. The megatron is an electron with the mass of a proton.
If it ever gets discovered, that's probably what they'll name it. But I don't know if that exists. Yeah.
There's like a whole YouTube channel that actually like takes things from like pretty much all the MCU movies and tries to make them in real life.
Really?
So they've actually like with Iron Man suits, like they've gotten actually pretty dang close with.
Really?
They've done like an assisted flight.
That's
They haven't
cool.
done the Hulk, but they've done some pretty cool.
They
It's
need
like
to do the whole
they've done Thor's hammer and it's actually insane.
Really? Wow, that's cool.
And they bought an entire warehouse and like actually made a logo similar to Stark Industries, called like Hacksmith Industries. And so they have this entire server room and then Jarvis, and it's this entire warehouse that's just for them to like play around with science.
Wow. That's, yeah, I mean, you really like, sometimes you think like that could never happen, but we have now things nowadays that like you wouldn't believe were able to happen. So that's cool. What's it called, Carter?
Hacksmith.
Hacksmith? I'll have to check that out. Okay.
The kids at home.
Okay. Now let's talk about everybody. Next topic here is where the radiation is coming from. Okay. So the radiation that our Geiger counter was detecting, there you go, okay, is coming out of the atoms, either like if I'm pointing at you and it beeps, it's coming out of you. The atoms inside of us, or the atoms in the world, go through a process known as radioactive decay. It naturally happens. Okay, it doesn't mean something's wrong with you, it happens to everybody. Anything with atoms can be radioactive because of this process. Now, once again, we know if it's going through an alpha decay, like we'll talk about here in a second, there's nothing we really have to worry about, right? Because alpha particles are harmful to us. And most of the ones that deal with inside of us aren't dangerous. But then, of course, once again, there are cases where they are. That's why another thing, like, have you ever heard of getting radon testing for your house? Right, so radon is extremely radioactive, so that can be really bad if you live somewhere and there's radon leaking into your house is because it's radioactive. Okay, so the idea of our decay series are actually very similar to that first activity we did of building a star, where all it is here is just a matter of balancing the numbers. Okay, the law of conservation of mass. That matter can't be created, it can't be destroyed. It can change, but that's it, okay? So, key thing with these problems is you want to pay attention to where is the arrow, because otherwise you'll get all your answers backwards. Okay, the arrow is our equal sign. So right now we have uranium-238. It's going through an alpha decay, which means it's kicking out an alpha particle from its nucleus. Okay, so if this is my nucleus right here, okay, protons, neutrons, right? Alpha decay means what? Throw an alpha particle out. Okay?
The paper didn't stop that, guys.
Now the big thing here is when we lose an alpha particle, we've just lost protons. What do protons mean to an atom? What it is. So when you lose protons, you change the element to something new, and that's what we're trying to figure out in these problems, is what is it turning into. Okay? Let's start with the mass first. Okay? So we have mass of 238. It's kicking out something with a mass of 4, so our new thing's going to have a mass of 234. Make sense? Okay, once again, follow the equal sign. 234 plus 4 equals 238. Okay, bottom number, we had 92 protons. I kicked out 2 of them, so now I only have 90 protons left.
Does that mean we can look at the periodic table and find the element that's 90?
Brilliant, Rachel. So look at the periodic table, find element 90. Thorium. TH. Questions on that?
Do we have to worry about the charge? Oh, there's not.
Nope. Actually, and with these, we actually won't ever deal with charges, because we're really just looking at their identity, how it's changing. And so it's really about the proton effect, right? Good question, though. Okay. Any questions before we go to the next problem? Okay, let's take a look at a beta emission. Okay, now side note, emission or decay means that particle is coming out of the nucleus.
Should we be writing this down?
It all just depends on it. I feel like you needed to help you. Okay, but it's just a word thing to be aware of. So if you read decay or emission, notice that that means it's coming out, which means it's after the arrow. There's going to be other ones where it comes before the arrow.
What does numbers must be on the notes? I don't know.
Must
I think I
balance.
Must balance.
Yep, the numbers must balance. Okay, let's take a look at our top problem here. Okay, so this is an example where a beta particle is coming out of the nucleus. Okay, so let's start with the top numbers. So it's 131. Beta particles don't have a mass, so our mass,
Is 131.
I'm going to write it right here because I can't write it there, stays the same, right? Beta decay, beta emission doesn't change the mass. Now, be careful here with the bottom number. Okay, once again, it just has to be balanced. So, -1 plus something needs to equal 53. So it actually has gone up in proton number.
And then 50.
Identify our element. Xenon. So remember, make a note, the bottom number tells you the symbol. Now let's pause for a second. How is this working? How does something come out of the nucleus, but then the proton number goes up? Anyone else feel like that feels weird? It should feel weird if you're thinking about it, right? Okay. So here's how or where a beta particle comes from. Okay? A beta particle comes from the process that a neutron, okay, so one of these little yellow guys, just gonna draw a little side picture to make a visual. There's more to it, but here's the simple explanation, okay? A neutron is like a proton and electron fused together. That's why they're neutral. Once again, there's more to it, but that's the basic idea. Okay? What happens in a beta decay is that a neutron, so one of these yellow ones inside the nucleus, splits. The electron comes out, and the proton stays behind, which is why it goes up in number. Okay, the more you understand the why behind these processes, the more it just all makes sense and you're not just trying to memorize a bunch of different things, right? Okay, questions on beta emission? Okay, let's go to positron emission. So same thing, mass is going to stay the same. Okay, because they have no mass. Bottom number this time now is going to be 18, because that's a positive one, which means our symbol is argon. Questions? Okay. Let's look at an electron capture. So here's the opposite word that Camille was when we were writing that down. Emission or decay means coming out. Capture means going in. So notice now that the electron or the beta particle is before the arrow. That's the difference. Which is going to change how you balance it, right? Now the mass-wise doesn't change. Okay, so the mass is still going to be 106 because they have no mass. But now that the arrow's over there, it's 47 plus -1, so 46. Which means its element PD.
Do you have them memorized?
The elements?
Yeah.
A lot of them, just because I talk about them so much.
Yeah.
Like, it wasn't ever anything, like, purposeful. It's like one of my weird random goals that, like, by the time I retire and I'm, like, a grandma, I want that to be, like, my cool grandma trick. Like, my grandkids come ask me, like, any element, and I can, like, tell them what it is.
I had a science teacher in like in junior high, and he's all like, I memorized the whole periodic table, but I never actually used it, so I'm not gonna make you memorize it. Yes.
Yeah, no, it's pointless to memorize, like, a lot of, you guys will probably find that you'll memorize a lot of the numbers just because you'll start using them so much, but it's not anything you, like, purposely try to do, right? So, okay, questions on balancing nuclear reactions? Now, the one we didn't talk about and we won't really see is gamma. Why would we not really have to balance gamma? Yeah, look at its symbol, right? What are the numbers for gamma? 0, 0. Right? Gamma doesn't actually change what it is, but it's energy that comes out in the process of a decay. So a lot of times gamma is present, but it doesn't change the nucleus, so we don't really, for now, focus on balancing it out. So, and then another vocabulary word, transmutation, is this process of becoming a new element. So in this case, when silver turned into palladium, that's called a transmutation because it changed into a new element. Any questions? Okay, let's practice it. Go ahead and turn to your homework packet for me.